I'm pleased to introduce the speaker, Kristof Denolf, and he's going to talk to us about the AI capabilities of the Versal, I'm going to get this product name wrong, sorry, the Versal product line. So if you all are familiar with that, it's a very exciting AI-enabled programmable fabric. By way of background, Kristof is pretty experienced in this field. He's done vision processing and computer vision applications for now AMD. His degree comes from, now I'm going to get this wrong, it's now part of the KU Leuven.
That's perfect.
There we go, close enough, huh? With an MS from Leeds Beckett as well, the PhD from the Technical University in Eindhoven. He spent over 20 years between IMEC, Philips, Barco, Apple, and then Xilinx, now AMD. His main areas of interest and focus is on cost-efficient design, video, vision, and graphics systems. So I'll pass it over to you.
Thank you for the introduction. Unfortunately, I first need to excuse my co-presenter, Bader, fell ill, so he's not here. So let's start by an example from the automotive domain and look at our modern cars. Modern cars are equipped with a wide variety of sensors, including cameras, and the data of those sensors, of those cameras, feed into computer vision algorithms, and then those computer vision algorithms provide advanced and hopefully intelligent functionality to the driver. The Versal device, depicted on the right-hand side of this slide, is a heterogeneous device well suited for these workloads. And you can actually see three compute complexes, three compute clusters on this device. There is on the left-hand side, the processor complex, the ARM processors, hardened. Then in the middle, in the blue, there is the traditional FPGA, the programmable logic. And then on the right is actually the part that I want to focus on in this talk, is the most compute-dense part of the Versal device. And we call them the AI engines. And as the name suggests, AI engines are good at accelerating machine learning workloads, but they're also good at other things. They're actually also good at things you might traditionally expect to land either in that programmable logic, like more image processing related application parts, or the pre-processing, so that we can, on the device, on the AI engines, accelerate the whole application. And this aspect is something that we already heard this morning that was touched upon by two of the presenters in the general sessions. So what we'll do in this presentation is we will first do a technological deep dive into and take a look under the hood, what are these AI engines? And we'll first take a look at the compute capabilities, but then secondly, and as importantly, we'll talk about how do we get the fuel to those engines? How can we enable concurrent data movement so that we can keep that compute, that we can keep those engines firing? And after we've done that, I'll introduce to you our Vitis Vision Library, which is an open source library. And in combination with our Vitis tool, this will allow the user to implement his vision processing pipeline on that Versal device and on the AI engines of that Versal device. And then before opening for questions, I will give you a sneak preview into the second generation of AI engines called AIE-ML. All right, let's deep dive. Let's jump in and focus on the AI engine. And it's actually an AI engine array. On the Versal core device family, you would find between 128 and 400 AI engines organized in an array. And these AI engines are well connected to each other so that they can well collaborate. They can either communicate if they are direct neighbors through direct connections, through shared memories or a stream. Even they can exchange, if they are neighbors, parser results through a cascade connection. But also when they are further away in that array, they can talk to each other through a axis stream interconnect network. So if you now go to the right-hand side of the slide and we zoom in onto a single AI engine tile, you see two parts on the slide. There is the gray part, which is the local memory, 32 kilobytes, completed with synchronization mechanisms and a data mover. And it's those data movers that are able to pick up the data from that interconnect network and then store it into the local memory, so that it then becomes available to the green part, which is the compute engine part of the AI engine tile. And that's where we find those vector operations that will provide us that dense compute that we're after. And it's not just a vector processor, it's a combination of a vector processor with a VLIW architecture, which means that within a single cycle, the compiler can schedule multiple operations, up to 7 at once. And what that allows us to do is, for instance, to make sure that you can load the data that you will need in the vector processing data path for the vector intrinsics. The whole goal in the end is to make sure that we can, as efficiently as possible, use those vector operations, the most dense operations. And what we actually will strive for is to have back-to-back vector operations. The last table on the slide that I did not discuss yet is to give you a feeling of the raw compute that the AI engine array. Let's take a look at the last column. So for 400 AI engines, and let's pick the data type int16. I'll come back to that in the next slide. All of those AI engines together will give you a peak performance of 13 tera max per second. And don't forget that the max is actually 2 operations. So, as kind of alluded to on the previous slide, a single AI engine. Oh, and before I continue, so in the next slides, I will focus on a single AI engine core and introduce some aspects of a single AI engine core. And then nearing the end of this section, I will open it up again to the whole AI engine array. All numbers that I present in these sections, so before the sneak preview, are all for the first generation of the AI engines. So a single AI engine core supports multiple data types. And what you can see on the left-hand graph of this slide is that, let's pick a data type, for instance, an int32 operand for a MAC operation, and compare that with an int16 by int16, you see that it quadruples. And then the same happens again if you would go to int8 by int8. So there is a quadratic increase when you start processing on smaller data types. The middle graph shows you that from a load store capability to the data path of the AI engine, there is actually a constant capability, which means that if you go to a lower data type, to a lower precision, you will have a proportional increase of the amount of elements you can store per cycle. And that's why an AI engine core in the data path has the capability to keep data local, so that whenever you go to smaller data types and you risk to become, for instance, load or store dominated, you can actually exploit data reuse and continue to operate on that locally stored data next to the data paths. And that's kind of indicated in the last graph or table on this slide. So in the next slides, I will give you an example, an intuitive feeling of how we can vectorize on the AI engine core, and I will do that for the int32 data type. At the end of the presentation, when I introduce the library, I will give you some measured results, and that benchmarking is done on smaller data types. So how do we program? If you would have the task to program a video processing kernel on a single AI engine, how is that done? The first thing that I want to point out is that it's a traditional software programming flow. So what we have done is we have built small wrappers around the vector intrinsics, around the vector operations, so that the kernel engineer can then actually program his vision or his video kernel in C++. And then he uses a single AI compiler, and we have a cycle-accurate simulator that allows us, the designer, to both check from a functional point of view, but also to do performance analysis, figure out whether indeed the performance lines up with his expectations. If not, he goes to the traditional flow to continue optimizing until he reaches that optimal goal, if possible, to have those back-to-back vector operations. The second thing that I want to show are 2 important properties of an AI engine core. So AI engine cores are built to support signal processing applications. And often in signal processing applications, as you can see on the left-hand side of this slide, is you find nested loops. That is why an AI engine core has the capability to do zero loop overhead on counters. Secondly, in signal processing, you often have input that is stored in an input buffer. You use signal processing operations, and the result needs to go into an output buffer, so you need to keep track of some buffer pointers. Also, that can be done without any overhead, so that we can enable a kernel optimizer to get as close as possible to those back-to-back vector operations. So let's try to make this a little bit more tangible by looking to a basic example that most likely everybody in this room knows, a two-dimensional convolution or in image processing called a filter 2D. You see a quadruple nested loop on this slide on the right-hand side because you have to produce the whole output width of the image, the height, and then of course you have to apply the filter kernel. And in this case, the figure shows it's a 3x3 kernel. So we want to vectorize this kernel, and the data type we have picked is that we want to exploit the fact that we can do vector operations on 8 elements at once. So before we go there, let's first unroll the inner loops of this kernel to simplify a little bit of the index expressions. After we have done that, we can now, instead of calculate a single output pixel, what we want to do is we vectorize in the horizontal dimension, so we can start calculating 8 output pixels at once. And so that means that since we're vectorizing on the horizontal dimension, we'll have to go in increments of a step of 8. So let's try to visualize it a little bit better. We want to produce 8 output pixels at once, and we need to apply that convolution, that filtering operation. What we'll do is for the first row of input pixels, for 8 values, we'll apply the first filter coefficient. Then we'll exploit on the data path, or next to the data path, some data reuse, and we'll move over to apply the second kernel coefficient on the next values. It's all multiply accumulate now, and we do that until we have processed the whole first row. And then we do the same thing for the second row of the filter kernel, and then the last row, until we have obtained the multiply accumulate of the 8 output values, and we can store it back in the output memory. So that was the part where we focus on the compute capabilities, but as importantly, of course, is the data movement. And the AI engine array is a data push system, and we rely on the DMAs to pick up data that is somewhere else in the system, store it into the local memory that is next to the AI engine core, and then we rely on synchronization locks. When all of the data is there, the core can start computing, the next data can already start flowing in, and now this pipeline is filled up, this concurrent movement of compute and data movement is happening, and we can drain then this pipeline until the whole output is generated. So this architecture allows us, because we have these synchronization locks, to support data flow style implementations. So that was for the single AI engine. Let's take a step back, zoom out to the system level, take a look again at the AI engine array, put back the knock-in so that we have the connection to the external memory where we can store, for instance, a 8 megapixel image. This 8 megapixel image is, of course, too large to fit into the local memory of an AI engine, which is only 32 kilobytes. So what we have developed is something we call a decomposing DMA, which allows us to chop up that big image in smaller pieces, in sub-images. And we add some metadata to those sub-images so that then we can send through the DMA those sub-images to the AI engine array that implements the vision processing pipeline, and the data can be kept local while flowing through that vision processing pipeline. And then on the other side, we have a composing DMA, we sometimes call it a stitcher as well, that then puts all of the sub-images back together to produce the big final output image. If you got a little bit lost in details, that's fine. That's why we have built and open sourced this Vitis Vision Library to support, together with the Vitis tool, the programming of the vision pipelines. And next, of course, to some host code or some framework code that needs to be developed, if we focus again on that filter 2D example, there are 2 major pieces in the library that I want to highlight. There is the aspect of the data movement, which I just introduced in the previous slide, that tiler and that stitcher, which we abstracted at a software level so that it can be easily configured to templatized parameters by the user. So that's one big piece. The second big piece of the library is, of course, a set of hand-optimized vision processing kernels that then the user can pick from and declare in his kind of vision processing graph. And then he puts all of this together and instantiates his graphs and kicks it off in the host code so that it can support his use case. The hand-optimized set of kernels I'll come back a little bit to it in later slide, is a continuously growing set of kernels that we're supporting. So, of course, we need a tool to be able to produce either the binary artifacts to run our application on the Versal device, or to run it in hardware emulation or profile it for analysis. And in the Vitis tool, you recognize color-coded the three major pieces we introduced on the heterogeneous Versal device in the beginning of the talk. In green, there's the AI engine array part again. In blue, there is the logic, the programmable logic, and those the data movers that I just introduced before will land in there. And then there is the host code that will run on the ARM complex. Combined with a hardware platform description, the Vitis tool is able then to generate all of the necessary binary artifacts to be able to then execute the user's vision processing application. So, relating it back to the previous slide and to the example we gave, what the user will have to do is he will describe his vision processing graph, picking some kernels from the vision kernels, so the green part of the library I introduced, and then combine that with the host code, compile it all together, and then it can run on the system. So we used this exact approach and these tools to benchmark some of the kernels that we have built. So on the horizontal axis you see a different set of important vision processing kernels, and we measured them. We measured their performance while they're processing 4K images. And you can see that for all the kernels on this slide, we are able to, even on a single AI engine core, because these are numbers for a single AI engine core clocked at 1 gigahertz, we are able to achieve real-time performance. You could actually kind of flip this slide, and what you could say is that you can combine multiple kernels together on a single AI engine core and still meet your real-time performance. So this is an overview of what we have currently in the currently released open-sourced Vitis Vision Library. So in gray is what is currently released in the 2021.1 release. And we have functionality, the typical basic functionality in the first column of this slide. Then we have all of the blocks you would typically expect to be able to support the machine learning use case, like normalization or resizing. The other thing we're actively developing is more and more support on ISP functionality, so to be able to deal with the raw pixels that are coming from the camera. And then finally, there's other functionality like filters or other things. And as you can see, in blue, we are planning to add much more functionality to this library. Okay, that was all about the first generation of AI engines. For the second, which is on the left-hand side of this slide, for the second generation of the AI engines, we have further increased the compute density. We have doubled the compute capabilities, and we have added support for other data types and also for smaller data types, which allow us to focus or better optimize the performance of the machine learning part of vision processing pipelines. Next to that, what we have also done, you might have noticed in the slide where we talked about the data movement, that we can fall back, we can use the ultra RAMs and the block RAMs of the programmable logic to build up a memory hierarchy. That has now also been hardened into the second generation of the AI engine in AI-ML, where we have, as shown on this slide, mem tiles. And so all of this combines allows us to further improve the efficiency of the AI engines with a factor of 2 performance per watt. So to wrap up, what we have done in this presentation is we have given you a deep dive into the AI engines of the Versal device and their compute capabilities, but also the capabilities to support concurrent data movement. We have introduced to you the technology we've built and then embedded in our Vitis library to decompose and compose and be able to have a data flow style implementation of vision processing pipelines. And then I introduced to you the open sourced vision library that allows users to implement their pipeline. And then on this slide, the resource slides, I have indicated pointer to the several aspects that I covered in this presentation. So I, of course, included the link to the open source where you can find the open source library for the Vitis Vision Library. But I have also included some pointers to where you can find more information about the AI engines themselves and about the Vitis tool. And if you have more questions, I'm ready for questions, but you can also visit us at the AMD booth, which is just right over there.
If anyone has any questions, we've got a microphone here. I'll tee one up while we're waiting. I had a chance to look at the slides, so it's easy. The Vitis library, the AI library, are they compatible with other AI development flows like TensorFlow and other frameworks?
Right, so the Vitis Vision Library is part of the whole Vitis tool framework, and they are completely compatible, for instance, with Vitis AI, which is our solution to support machine learning use cases, and then indeed to achieve the goal of accelerating the whole application and the whole vision, for instance, in this example, the whole vision application pipeline. Yes.
Other questions? I'll just keep going. Okay, let's go another one. The AI core is described as a 32-bit scalar RISC with a 512-bit vector engine at a gigahertz. So I guess two questions. Is that a hard core? Is that a soft macro running on the fabric?
Right, so like the processor complex on the Versal device, the complete AI engine array is hardened. The only soft fabric that is there was the middle part, which I called the programmable logic.
So that's how you hit a gigahertz.
And that's why the AI engine array runs and is sampled at 1 gigahertz, yes.
And then let's see, follow-on question. What's the architecture? You said it's a RISC core. Is it RISC-V? Is it ARM? Is it microblaze?
I think you're talking about the scalar processor.
Yeah, the scalar core, yeah, sorry.
To be honest, I'm not 100% sure, but I think it's something very, it's none of the other things you mentioned.
Specialized RISC-V core.
Right.
Hi, this is Riyadh from OmniML. If someone wants to optimize a model for this hardware AI engine, what type of hardware properties we can use?
Can you repeat the last part? If someone wants to optimize?
If someone wants to optimize a model, what type of hardware properties we can use? Like what type of hardware properties we should look for to optimize a model?
And you're talking about a machine learning model?
Yes.
Okay, so I'm sorry, I couldn't hear you back here. So for the support of machine learning use cases, you would be able to fall back on the Vitis AI part of our solution. You can start from whatever your favorite framework is, and then you can, there are different techniques that allow you to map your machine learning network onto the AI engine array. And we actually have also a model zoo out there. Yeah, I think if you start from the AI engine resources on the right, you will find it.
Any other questions? Let's see. All right, so where's the power profile on this in terms of watts, right? From an embedded vision standpoint and an edge standpoint, the market often is the further towards the edge you go, the more power constrained the device is. So where does this product fit from that standpoint?
So in good old-fashioned Xilinx tradition, this is a product family, of course. So the numbers I had in the beginning of the presentation were for the Versal core, which are typically bigger devices with a larger power consumption, but we also already announced the Versal edge devices, which would be much more suited and have a much lower power budget for edge-alike applications.
Any other questions?
Yeah, I just had a question about HBM memory. I know that a few years ago, Xilinx started rolling out devices with HBM memory similar to some of the GPUs. Is it in the product path for devices with the ACAP?
So you might have noticed that on the initial slide when I introduced the Versal device, we have a NOC there, and then underneath the NOC we had all kinds of connection capabilities, and HBM would be one of those.
For your network on chip DMA transactions, how many of those concurrently can be happening to your external memory from your AI engine over your Versal engine?
So I don't know the number by heart, but the answer is many because we have multiple channels on the NOC that then you can connect to the external memory to sustain a sufficiently high bandwidth.
And who's controlling those DMA transactions? Like who sets them up and knows when they're complete?
So that would actually be by configuring, by setting up the DMAs in the AI engine array. Another possibility that you could rely on is to go through and build your own dedicated data mover in the programmable logic, which is then also connected to the NOC, and in that way then you can also reach the external memory. Actually, when I introduced that decomposing and composing DMA in the current solution that you have out there, that lands, those are specialized data movers that land in the programmable logic.
So the scalar and the vector pipeline, are they share the same pipeline or they have a different pipeline?
The scalar processor and the vector processor, are they working in parallel? Is that your question?
Are they share the same pipeline or they have a different?
No, they are
sharing the same pipeline.
Anybody else? Okay, Kristof, thank you. Please join me in a round of applause.
Thank you.